Wasabi, you guys. Welcome to Integration B Training for Intermediates, Part 14. I'm trying to not lose track. In this section, we're going to do decisive integration by parts. This is the most annoying integration by parts technique. Well, it's not really a technique, it's more of just practice and experience with annoying integrals that mostly show up in a lot of integration Bs. So let's dive right into it. You might have seen me do this one, but if not, here it is. This is an annoying integral. Now, decisive. Why is this a decisive integration by parts? The reason I call this decisive is because there are so many ways. There are different paths that you can integrate by parts. You can either derive and integrate this. You can derive this and integrate this. Or you can derive this and integrate this. But here's my question to you. Which is faster? Which path is faster? So that's what I'm going to be showing you in this section is which path should you try? And I'll kind of give you sort of an insight of how I do it. So, out of all these three choices, the fastest for me, at least, is this one. This is the fastest for me, and I will show you why I chose this one. So, I derive this, sine of x. This is cosine of x, that's sine of x. Because I know it's going to be recursive. Here, I want to integrate this because it's a lot easier, because this is just x e to the x minus e to the x. If you remember your integral, 10 integrals that you should memorize for integration B, this is one of them. And all it does, it just adds, not adds, but just another minus e to the x. That's all it does. And if I do it again, it's a lot easier for me to just integrate again. Because, you know, all it does, it just adds another negative e to the x. Okay, so then this and this is my answer. But then what about this? So now the way I write it, let me go ahead, delete this whole thing. So this, I'm going to call this I. And then this whole thing, I'm just going to be lazy about this. I'm going to factor e to the x out. I have sine of x, which is x minus 1. And then I have minus cosine of x with x minus 2. And then here, oh, this should be negative. Here, I have minus I, because this is the same thing as that. But then we also have plus 2 e to the x sine of x. This I am okay with because I know what this integral is just by memorization, right? I think I put this as one of the 10 integrals to memorize as well, but I don't fully remember. But this I right here, we could just add it up, 2y, and then this is equal to e to the x. It's a half, but this half gets cancelled by this 2. So this whole integral as a whole is just e to the x sine of x minus cosine of x. Okay, and now we could bring this 2 and divide it. We just divide it. So now our original integral, e to the x over 2. This sine of x gets added. So I'm pretty much, again, factoring the e to the x out. And I get 1 more here. And then I got minus 1. Ooh, let's see. This will go, let's see, negative cosine. Don't forget that there's a negative here. So technically it would be like cosine of x 2 minus x, right? And then this adding a cosine would give me 1 minus x. So Oh, hold on, that's a little annoying. So adding 1, this cancels out, so it will just be x sine of x. I was gonna write sine of x times x, and that looks uncomfortable. And then minus cosine of x, x minus 1, because of this negative here and this negative here. That makes this positive 2 cosine of x. So be very careful with that. It's not x minus 3, it's x minus 1. And then that's pretty much it. This is our integral. Okay, I think the last time I did it, I was very lazy, so I wrote it as a long answer, but I believe this is what it is. Whew. Okay, now what? What are you gonna do? If I, let's say, you know what I used to do back then is the way I kind of train my friend to do very fast integration by parts is I would always give this integral and sort of test them if they can solve this under 2 minutes, telling them how fast can you integrate by parts. How fast can you integrate by parts? If you think you can if you think you can integrate very fast, integrate by parts fast, try this, and good luck. It's not easy when you haven't seen this integral before, but if you have, then you sort of know kind of the route that almost a lot of people would take. And what is that route? Is it this, derive and integrate, or do we derive this and integrate this? A lot of you might choose here by instinct because, I mean, that's an ln of x. We definitely don't want to integrate this, right? Sometimes well, rarely actually, but here, this is the correct choice. This is what I would do at least. And the reason is because, I'll show you. I think it'll be understandable if you see this. We have inverse sine of x. This is x inverse sine of x. This would be like plus square root of 1 minus x squared. I didn't memorize the answer. I'm doing the process in my head. And then here, if you notice that when we do the integral here, right? Notice that this becomes inverse sine of x again, right? That's what I would rather do this, because when we integrate, I mean, I've already integrated inverse sine of x. If I need to do it again, I could just look at this, right? I don't have to think about it. So that's very good, and that's the thing that I would take advantage of. So with that, first let me go ahead and write my solution. ln of x, this, and then here, well, minus. So minus integral. We get this, which is all what we have, and then 1 minus x squared over x. So now all I have to pay attention is this portion. Here you could just sort of factor it, because this is just this, so you can sort of go like this. Right, this is a minus 1, because it's the same integral. Okay. But here we do trig sub, right? Let x equal sine theta. And this becomes cosine square theta sine theta d theta. Right? So now we have, this becomes 1 minus sine square. This portion here becomes 1 minus sine square. So now we have cosecant theta minus sine theta. And this will be, we have this negative, so I'm just kind of distributing it. This is annoying. So now what we have is this whole thing, this long answer, and then we have this distribute the negative, this here. Well, x is equal to sine theta, so theta is equal to inverse sine of x. Cosine of inverse sine of x, we kind of went over that through one of our past videos. This is 1 minus x squared plus the ln of cosecant theta. Cosecant theta is 1 over x plus cotangent theta. Cotangent theta is cosine theta over sine theta. So that's x cosine of inverse sine of x is square root of 1 minus x squared. And that is our answer. Oh my god. So, again, this integral, this integral, this integral, this is an ugly integral. As small as it looks, it's nasty. So, this would be our answer. This is a minus 1. 1 minus x squared. Yep. That's pretty much it. This is a very common one. You'll definitely see this a lot in integration bees. So, what do I do with this? Do I derive inverse sine of x? Or do I integrate inverse sine of x over square root of 1 minus x squared? What do I do? The easiest path you should always choose is this. Right, now this is negative 1 over x square root of 1 minus x squared. Here, this is actually a u substitution, and this gets you negative square root of 1 minus x squared. Look, this integral here, it just becomes 1. So now this whole integral just equals to x plus, I'm sorry, not plus, minus, there's a minus here, inverse sine of x square root of 1 minus x squared plus c. And that's it. Oh god. Another one of these. It's like inverse sine of x ln of x, but this is different. So what do we do? What's your decision? Do you want to integrate inverse tangent of x or integrate ln of x squared plus 1? We would rather derive ln, right? Because we don't like logs when it comes to integrals. So we'll definitely integrate inverse tangent of x. Here this is just 2x over 2x squared plus 1. Here this is x inverse tangent of x. I'm doing the process in my head. Let's see. We have this, we have, we get x over x squared plus 1. And so this would become minus a half ln of x squared plus 1. I don't know why I put absolute value, that's just a habit. So, and would you look at this? This is actually very nice. So we have our answer here, but if we kind of look at the integral, the 2 cancels out, and the negative cancels out here for this term. So we have ln of x squared plus 1 x. Let me actually rewrite this. That's actually a very nice u substitution. This is a very nice u substitution. And here you get minus 2 x squared over x squared plus 1. We've dealt with this before, right? This is like plus 1 minus 1. So we get like 1 minus this, right? That's nice. That's very nice. Now this is just inverse tangent minus inverse tangent of x over x squared plus 1. That's what that is. Let me clean this up a little bit. Okay. So now, this is an easy u substitution. Half, let u equal x squared plus 1. And then, let's see. Well, technically you can let u equal ln of this whole thing, ln of x squared plus 1. And then you'll get u squared over a half. So this is 1/4 of ln square x squared plus 1. Okay. And then here, oh, well this is the same integral as this, so we can actually factor it with this. So I'll do with this later. And then here, this is plus times 2. Plus times 2. Oh, well, let u equal inverse tangent of x. This becomes 2u du. So this is inverse tangent square. And then here, with the nasty stuff, we could just go like this. Minus 2. Because of this, the integral of this, and the integral of this. We can just sort of factor it, and then we get this. Nasty. Nasty answer. And a plus c here. And then now this is our answer. And there you go. Ugh. Disgusting. Honestly, with anyone who gets integrals like these with a definite bound, I am so sorry for you. Either not only that you get a long answer, but you have to plug it in, the bounds, and sometimes the bounds can be points that are not really defined by a function. So most of the time when you have a definite integrals like these, you're gonna have to do like limits and stuff, because most definite integrals with these decisive integration by parts integrals, they're mostly improper. Okay. So thank goodness we don't have a definite integral. Honestly, no one should have to go through that, because that's just lame. Here, inverse hyperbolic secant or inverse sine. Not that many people knows the derivative of inverse sec, so that's okay. But to let you know, this is the derivative of this is negative of 1 over x square root of 1 minus x squared. Okay? That's what that one is. So, are we going to derive that or integrate? Well, we're definitely deriving this, because I don't know if I want to integrate that. So, let's go ahead and derive this. Well, this becomes positive. And then integrate this. We've seen this a lot of times. We'll just go ahead. And this would be minus, right? No, plus. Okay. Now would you look at this? When we put it in as an integral, this goes with this, which is an easy u sub, and this goes with, oh wow. You see how I don't really have to really have to write the integral out. I could just see it in my head. Oh, this is a u substitution, this is just 1 over x. Right. So now I could actually just go ahead and dive straight into the answer. This is here. This would be a half of inverse sine squared. And then this is just ln of x plus c. Alright. Whoa. Now we have an MIT style integral. What is this? What do we do here? So for me, I would derive inverse tangent. And the reason is because I can easily integrate this. Right? If I were to choose which one's easy integral, this is my easy integral. This is easier to integrate because if you think about it, if you integrate this, x squared plus 2x plus 1, oh, this here is a product rule, and then plus e to the x. So that's how I kind of see it. So let's go ahead and integrate by parts. This becomes x squared and then plus 1. Oh wow, x squared plus 1 cancels out. And so it's just minus e to the x. Alright, well there you go. That's my answer. And then minus e to the x plus c. There you go. Alright, here is our last integral. What are you going to integrate by parts with? Because this looks like an abomination. Now you're probably thinking, okay, there's a bunch of this and that and this and that, you know. How do we, which do we integrate, which do we derive? So, I'm actually trolling with you. This is, you don't do decisive integration by parts. Don't overuse it. Because, I mean, well, it probably doesn't look like a bunch of 3 different functions or 2 different functions. So, and if you spot that, that's good. You don't have to sort of go with other people's advices. You know, when they say, oh, use decisive integration by parts if you want. No, if you see something faster, do it. So, here, the actual fast way, what I would do is let u equal this. Now, this is very hard to see. I understand. You're probably thinking, how the hell? Like, what is the motivation behind this? Well, it's mainly because I've been integrating a lot. But here, when you do du, this, if we do product rule, you get ln squared plus 1. And then here, when you derive this, this is 2 ln of x, all 1 over x, but it gets cancelled out by this x. And so this is your du. No, I'm sorry. Yeah. So this gets taken away. So this is just the integral of u du. Right? But that's very hard to see. That's very hard to see. I don't blame you. I don't blame you. It is very difficult to see. But that's, if you ever come across this, this is the fastest way. Now, or something similar like this, then that's where you can experiment, let u equal a bunch of ln of x functions, and then just see what the derivative is. You'll be very surprised. A lot of x times ln of x's, it becomes a ln of x polynomial. Because, I mean, we're so used to knowing the derivative of this, right? If we derive this, then this is ln of x plus 1, right? So x times some ln, a function of ln of x, like this, then your du is going to have like a polynomial of ln of x's. Because this x is going to cancel out the 1 over x chain rule. So that's why if you see something like this, there's like an x in front of it, let u equals x times some function ln of x. So that's a very advanced, sneaky trick for you. Okay. So with that tip aside, as a beginner or intermediate, it would be understandable if you let u equal ln of x, because there's so many ln of x everywhere. I'm more comfortable with e to the u. That is totally okay. In fact, I would actually support this because it is a lot easier to see. So now here, you could possibly simplify this. We get e to the u, well, we have e to the 2u, technically. And then u squared plus 1, u plus 1 squared du. But what do we do here? What on earth do we do here? Integration by parts? Okay. Let's actually split the e to the u. U squared plus 1, e to the u, u squared plus 2u plus 1. Because we've done this before, this was like e to the u, u squared plus 1, right? And then here this is, oh, wait a minute. Huh. So this doesn't work. This does not work. Like that? I don't know if you want to keep going. Anyways, if you ever see x times in a bunch of element functions, try this. Try it. Let u equal x element of x, or, well, obviously not, but you can try x squared or this because of this, and then see if whichever works that fits the du. Okay, so that's this is my biggest advice here. All right, so this is integral of u du. The answer would just be half of x ln, I'm gonna put parentheses. There you go. So that's it. That's decisive integration by parts. Very ugly, but now that you're aware of these ugly integrals, you at least know the fastest way. So I hope you find this helpful, and yeah, thank you so much for watching, and I'll see you guys in the next part.